Hello everyone, we are Team 7, and today we will introduce our Industrial Internet of Things predictive maintenance method in automotive manufacturing plants. This is an overview of today's presentation. The automotive industry has an astronomical financial weight in world economy. 78 million of cars are projected to be sold worldwide in 2020. The extensive amount of car sales come along with massive amount of manufacturing needs. In a manufacturing plant setting, maintenance costs are estimated to range between 15 to 40%. Therefore, maintenance management is undeniably crucial for automotive manufacturing plant operation. For the purpose of this project, the team decides to focus on one specific process in the assembly line to implement our novel maintenance method. Resistance spot welding is one of the key aspects during the manufacturing process. It is extensively employed in automotive assembly. In the area of information, the industrial IoT, which connects physical devices, began to transform the manufacturing maintenance framework. The maintenance system built on top of the industrial IoT network is expected to reduce cost, minimize downtime, and optimize equipment reliability. Under all the reliability-centered maintenance philosophy, preventive maintenance and predictive maintenance are the most favored method. However, an estimation of 57% of the plants are still using run-to-failure method as of 2018. This conventional reactive maintenance method prompts many issues. For example, the company will experience unscheduled downtime in machine production availability and incur extra cost. It may also affect product quality and worker safety. Currently, two greatest obstacles for manufacturing plants to improve maintenance are lack of resources or staff and lack of understanding of new maintenance methods. The team saw the advantage with predictive maintenance and determined to create a new industrial IoT predictive maintenance method that utilizes the machine learning model. The product should go beyond traditional predictive maintenance in terms of ease of use, cost, and reliability. It should also contribute to the product's quality and eliminate the inefficiency during product quality checking. For example, the traditional way of testing the quality of RSW uses sampling inspection, which is incomprehensive and insufficient. Hence, the team believes the product should not only help the company save money and time, but also indirectly improve the production quality.
The core idea of our design solution is actively monitoring welding quality to achieve customized maintenance planning. To achieve this, we first need to enable the industrial IoT environment. The team devised three major design components. We determined the design should have first the data infrastructure to extract and load manufacturing data. This is followed by second, the core machine learning model to make prediction on the product's weld quality ranging from good, recoverable, and poor. Finally, the solution will be consolidated with a user-friendly dashboard to make meanings out of the data and schedule active maintenance planning. To start things off, we will start from the very beginning of the data process pipeline, the sensor data extraction. The team first identified the required sensor data, then based on their data types, devised machine groups to extract the data from. The required data were chosen based on their impacts to the quality of the welded product, as well through benchmarking research articles. Welding current, time, and force are given by microcontrollers embedded within the RSW unit. Machine vibration is given by displacement sensor installed to the machine unit. Operating surface temperature is given by infrared thermometer installed at a fixture aiming towards the surface of the welded product. Finally, electrode material along with the treatment applied to it will be given by the mechanic a data entered through a line PC. Each machine group's data can be accessed by their programmable logic controller, a middle bridge between hardware and software. The team will extract data from their respective PLC machines and store into an internal SQL table, which is a highly standard method of handling manufacturing process data. Now that we have sensor data extraction, we will consolidate the data through a robust data pipeline. Sensor data are now stored in internal SQL tables. and to further derive a label dataset required for the core machine learning model to thrive, those internal SQL tables are merged into a centralized SQL database. In parallel to this step, final verification stage and quality checkup stage are used to formulate an independent SQL table containing final product status. This is referred to ground truth table, where it contains answer to the questions the model is trying to solve, which is predicting the final product status given the input parameters. The two tables are interjoined to create a centralized SQL table, which consists of both the input parameters and the ground truth label. This is how the schema of the final consolidated data will look like. It's a combination data between sensor and the label. After training, for prediction data, the pipeline will only pass the sensor data and let the model populate the label data with its predictions based on trained parameters.
Now, I'll give a walkthrough of the machine learning model, which is the second section from our design. The model will be using data collected from earlier stage as the input, which includes RSW machine-related statistics and welding process-specific information. It will make prediction of the product quality by using the real-time data feeding. To find the optimal algorithm for quality classification, the team refers to multiple previous studies in the manufacturing field. There is a research showing that among different supervised classification models, the deep learning neural network, DNN, has performed efficiently in both prediction accuracy and speed. Therefore, we propose the DNN model to be implemented for RSW product quality prediction. Another highlight of the design is the seamless model update process. It's enabled by having separating prediction and training data pipelines, which ensuring online prediction operation while conducting offline model retraining and validation. Once we have the quality prediction generated by the model, process engineers are now able to make informative maintenance decisions. There are multiple quantitative evidence are output by the model, including frequency of product in a particular quality class and the trend of quality changes from day to day to identify sudden or abnormal behaviors.
A reliable data infrastructure and advanced algorithms are crucial for our solution. However, without an effective way to communicate with its end user, the impact of our solution will be greatly hindered. That is where our front-end software comes into play. The main panel of the user interface will be a live monitoring dashboard with collected information from the machine status sensors and central computation server. As shown, the dashboard will constantly monitor and display failure rates of each machine lines, and in addition, the plant engineer will be alerted when there is an abnormally high failure rate. The process engineer then will be able to quickly issue work orders to the maintenance team to ensure the machine will be inspected immediately. To quantify the impact of our solutions, the team has conducted a series of numerical analysis. The downtime cost reduction is a major benefit of predictive maintenance. On average, manufacturers experience around 800 hours of downtime annually, and the cost of downtime for a typical automotive plant is $22,000 per minute. According to the research, the predictive maintenance system can deliver a 35 to 45% reduction in total downtime. Hence, a fully implemented predictive maintenance system can reduce a manufacturer's total downtime cost by $380 million. Please note that 90% here represents the spot welding machine composition within the automobile assembly process. Another significant cost reduction comes from equipment maintenance. In general, the plants spend around $30,000 on maintenance for each $1 million of their asset value. The study has concluded that predictive maintenance results in a 64% maintenance cost reduction on average. Born in 2019 total asset value of Ford Motor plants, we can get a $630 million maintenance cost saving in total. Although the long-term benefits of our solutions are undeniable, its limitations are also prominent. A properly implemented system requires expertise in the fields of machine learning and industrial IoT, which is not a prevalent case in the traditional manufacturing environment. Also, the high initial cost of implementation can also be a huge financial burden for the organization. These limitations make the early implementations extremely challenging for the plant. Therefore, carefully planned early stage is crucial for the success of our solution. Indeed, the current solution will bring tremendous benefits to the manufacturing plant once it's properly implemented. The team, however, would like to propose a few future areas that engineering team continues to work on. Firstly, the current algorithm classifies product quality into 3 categories. This categorization can be further refined to capture more subtleties among products. Secondly, the system can be made more modular to be compatible with more machine lines, hence enable a more sophisticated and comprehensive functionalities of the software. Finally, the action recommendation functions of the user interface is quite rudimentary at the current stage. It can be further expanded to include more intelligent and diverse actions. For instance, process engineers should be able to issue inspection with specific maintenance advice based on the machine status provided. Clearly, with the help of predictive maintenance systems, the resistant spot welding line at the traditional manufacturing plant can be completely transformed. The solution will bring around $1 billion saving associated with machine downtime costs and plant maintenance costs for a major automotive plant. Besides fiscal benefits, our advanced maintenance solution can certainly lead to a great improvement in worker safety and in product quality, which translates to manufacturers' ultimate goal, client satisfaction. We hope you enjoyed our presentation, and we look forward to your feedbacks.